Welcome to today's class on functional analysis. Today we discuss Hahn-Banach separation theorem, and for that we first discuss a supporting lemma. That X be a normed space over K and F be a non-zero linear functional on X if E is open subset of X, then F of E is an open subset of K. Proof: since F is non-zero, there is some A in X such that F of A equal to 1. Since if F of D is equal to some K with K not equal to 0, then 1 by K F of D, this is equal to 1. So this implies F of D by K equal to 1. So you can let A to be a D by K. So this implies F of A equal to 1. So if F is non-zero, you can find some A in X such that F of A is equal to 1 because F is linear. Let A not equal to 0 and X belongs to U. Now since E is open, there exists some R positive such that U of X R is contained in E. Now if modulus of K is less than R by norm A, then X minus K belongs to E. This is because since norm of X minus K, this is equal to the norm of K, which is less than, since modulus of K is less than R by norm A into norm A. So this is equal to R. That is norm of X minus K is less than R. So this implies X minus K belongs to UXR. This is the reason. So if modulus of K is less than R by norm A, then X minus Ka belongs to E. So we have F of X minus K. This is equal to F of X minus K into 1. So this is F of X minus K into F of A because F of A is 1. So this is F of X minus F of K because F is linear. So this is equal to F of X minus K. And since X minus K belongs to E, we have F of X minus Ka belongs to F of E. This belongs to F of E. This is because since X minus Ka belongs to UXR, which is contained in E. So if modulus of K is less than r by norm, then f of x minus k belongs to f of e. We consider k dash in k such that modulus of f of x minus k dash is less than r by norm. Then you know f of x minus k dash. So we have f of x minus k dash belongs to k. So you can let k equal to f of x minus k dash. Then this k satisfies, so this implies modulus of k is less than r by norm. R by norm. So this implies f of x minus k belongs to f of e. So here k is f of x minus k dash. So this implies f of x minus k is f of x minus k dash. F of x minus k dash belongs to f of e. So this implies k dash belongs to f of e. That is, set of all k dash in k such that modulus of f of x minus k dash less than r by norm is contained in f of e. And you know this is an open ball with a center f of x and radius r by norm which is contained in f of e. So you have, this is the situation, suppose that you have, this is f of e, then you consider f of x here, then you can consider a ball with the center f of x and radius r by norm. So this is an open ball because it is less than. Therefore, f of e is open. Now we prove Han-Banach separation theorem, theorem 7.5, proved by Han in 1927 and Banach in 1929. We state this theorem: let X be a normed space over K and E1 and E2 be non-empty disjoint convex subsets of X, convex subsets of X, where E1 is open in X. Then there is a real hyperplane in X which separates E1 and E2. E1 and E2 in the following sense. For some f in X12, and T belongs to R, we have a real part of f of x1 less than T less than or equal to real part of f of x2 for all x1 in E1 and x2 in E2. This is Hanbanach separation theorem. So we prove this. Proof. We have the set E1 minus E2 is equal to set of all x1 minus x2 such that x1 belongs to E1 and x2 belongs to E2 is non-empty and convex. Since E1 is open by 5.6a, you know E1 plus E2 is open, or E1 plus minus E2 is open. E1 plus minus E2, that is equal to E1 minus E2, is open by 5.6a. Now since E1 and E2 are disjoint, since E1 intersection E2 is empty, we have 0 does not belong to E1 minus E2. So you let y equal to singleton 0 and E equal to E1 minus E2 in theorem 7.3 that we have discussed in the previous class. Then by the theorem 7.3 there is a sum f in x12 such that real part of f of x1 minus x2 is not equal to 0. Because here E is E1 minus E2. This is true for all x1 in E1 and x2 in E2. Therefore, real part of f of E1 and real part of f of E2 are disjoint, convex subsets of R. Hence, they are non-overlapping intervals because it is convex subsets of R. Hence, they are non-overlapping intervals in R. So we can assume that they are intervals which are non-overlapping. So you can assume that this is a real part of f of E1 and real part of f of E2. So assume that real part of f of E1 lies to the left of real part of f of E2. So we can assume that real part of f of E1 lies to the left of real part of f of E2. So if it does not happen, you can replace f by minus f. Upon replacing, f by minus f if necessary. Now, a real part of f from x to r, this is a function from x to r, is a non-zero continuous real functional on E1. Is a non-zero continuous real functional on E1. And E1 is an open subset of X. Therefore, by lemma 7.4, the previous lemma, so by lemma 7.4, the real part of f of E1 is open. So it is in fact an open interval. Is an open interval. If T is the right endpoint, of a real part of f of E1, so that is, it is here, right endpoint. So this is T. F of E1, we see that real part of f of x1 less than T, less than or equal to real part of f of x2 for all x1 belongs to E1 and x2 belongs to E2. So this proves Harmonic separation theorem. Geometrically, the preceding separation result says that set E1 lies on the one side of the hyperplane set for x in x such that the real part of f of x equal to t, and the set E2 lies on the other side, since E1 is contained in set of all x belongs to x such that real part of f of x less than t and E2 contained in set of all x in x such that a real part of f of x greater than or equal to t. So that's all for the day.